Hello everybody, nice to see you again. This is Professor Bajigni. Today's lecture is the continuation of chapter 4. Here is an example of 4.2. Consider the circuit in figure 410. So we have the circuit shown here. What we are given here, we are given the value of the resistance R1, R2, and R3, and also the voltage. So this circuit has more than one resistor. So, and those resistors R1 and R2 and R3 are connected in series. So what we are asked here to find the total resistance. Again, what is the total resistance formula? RT is equal to the sum of the resistors R1 plus R2 plus R3. So we have the value 10 plus 16 plus 24. So this will be total of 50 ohms. Okay, after that, then we can convert actually this circuit into one circuit, simple one with one resistor, which is RT, and we have the current flow in this direction here, I. So simply, if we apply Ohm's law, we have V equal I times R. We need to find I. So we divide both sides by R to get the current. So current equals V over R. Now we are given V, which is 60, and we know R in this case is RT, which is 50. So simply we just apply again Ohm's law, since this is Vs or V, whatever the symbol of the supply voltage we can use. Then after that, it will be easy to determine the voltage across R1, R2, and R3. And as we mentioned earlier, that these voltages across the resistance, they call the voltage drops. These voltages will be consumed by the resistance. So we have a supply voltage, 60, and then we have the voltages consumed by these three resistors. Now, according to the conservation of energy, that the voltage applied or supplied to these three resistors must equal to the total voltages consumed by these three resistors, or the total voltage drops. Again, the beauty of Ohm's law, V equal I times R, can be applied at any resistor. So if we come to this resistance R1, we need to apply Ohm's law, so it will be I times R1. Okay, here's the formula. V1 is equal I times R1, and since I is the same through R2 as well R3, then V2 will be I times R2, and V3 will be I times R3. Now, if you want to check, we can do the following. We can check that the supply voltage must equal to V1 plus V2 plus V3. Let's check. We have the supply voltage at 60 volt. Okay, and how about V1? V1 is 12, and V2 is 19.2 plus 28.8. If we sum up this, we will get 60 volt. Okay, so this is a rule that the supply voltage must equal to the total voltage drops. Again, remember that the rules of when you solve any problem, you need to write down the Ohm's law and the power formula. So Ohm's law is V is equal I times R. We can use this formula at any resistors to find the voltage drop, or to find I, or to find R, whatever the information we're given. So if we are given two informations in this equation, we are able to find the third one. Then we have the power formulas. How many of them? We have V times I, we have I squared times R, and then we have V squared over R. So whatever is convenient for us. So if you want to find P1, the power dissipated or consumed by the resistance R1. So P1 will be equal I squared times R1. And now in the book here, he used the IV. He used this formula. It's fine. We can use either one of these because in this case, if we use the formula as the book used, we said P1 equal V1 I1. So we have to be specifically finding the voltage across R1 and the current through the I1. Okay, we cannot use this voltage, for example, or this voltage. We have to use the voltage across the resistance that we are trying to find the power dissipated at this resistor. Okay, the same thing when we come to find P2. Again, we have the option to use I square R2, or we have the option to use I times V2. Okay, we have to use the same voltage across the resistance that we are looking to get the power consumed by that resistance. We cannot use V1 because V1 is related to R1. We cannot use V3 because V3 is related to R3. And we cannot use Vs because Vs is the supply voltage to all of these three resistors. The same thing or we can use also the third formula. P2 is equal to V2 squared over R2. And since we have V2, we determine V2. So again, there is a lot of, either one of these formula, IV or V I square R or V square over R, we can use to determine. Now, to find the total power, there's two ways to find the total power. We know that the total power coming from the supply, okay, the supply power is equal to the sum of the power consumed by the three resistors, so P1 plus P2 plus P3. So we are given all these value here. So if we add this together, we get PT. Or another way we can get PT also is equal to I times RT. We have an RT and we have an I. So this give us the same answer as if we use this formula. So 1.2 times 50. They give us the same as 72 watts. So maybe this is a faster and easiest way to do it, or you could use these two here. It doesn't matter. Okay, if you look to a practice problem 4.2, we are actually given the same, if we just follow the same steps as we did in the previous example, we can find whatever we are looking for. So we're given actually 4 resistors here. Total resistance, again, RT equal to the sum 1 plus 8 plus 12 plus 4. So we should get 25 ohms. Okay. The current, again, if you look these here, all this, the sum of these 4 here is equivalent to RT. So we can redraw the circuit as follow. We can draw it as follow here. We have the power supply, and we replace these 4 resistors into only one resistor. So it becomes a simple circuit with one resistor and one power source. So this is an RT equals to 25 ohms. And this is the 50. So here's the current I. So I, according to Ohm's law, is V over R. Again, write down the information that we talk about it. Ohm's law, I times R, power, I square R, V times I, V square over R. Always have this ready next to you so you can use them whenever you need them. Okay, so find I. Okay, I is voltage, 50 over 25 is 2 amps. Okay, so this is 2 amps. Now we go back and apply. See, we can use Ohm's law in many, at any of these components. This component, this component, this component, or when we combine this component, also we can use Ohm's law. Now we go back to the circuit here. We know I here is equal to 2. And we know if we apply the Ohm's law across R1, so we can determine, okay, V1, which is again I times R1. I is 2, R1 is 1, so this will be 2 volts. Same thing, V2 is the current here, same current flowing in all of them here. Current is going to loop around. So it will be V2 is equal to I, which is 2 times 8 will be 16 volts, and so on. Now you can check again, as I mentioned, that V, which is 50, V supply equal to V1 plus V2 plus V3 plus V4. And you'll find out that if you add those voltages, the left-hand side is 50, and the right-hand side is V1 plus V2 plus V3. If you add up all of this, you get the power. Now, the last one, how to find the power delivered by the source. Okay, now I want to explain to you what is the difference between the power delivered by the source and the power consumed by those resistors. So whenever there is a power supply, we can get a power out of the power supply. That power must equal to the power dissipated in these 4 resistors here. So PT, or the power delivered by the supply, is equal to the V times I. Remember one of the form V times I? Now which V here? This V here, because we're looking for the total power of the power supply. So whenever we apply the power formula, we always look to the voltage across that component, and the current goes through the component. So the current is the same in this circuit here. Current the same through the 50 volt, sorry, and the same through R1, same through R2, R3, and R4. So now, since we are using the power delivered by the source, so we have to use the voltage of the source and the current that passes through the source. So it will be 50 times the current is, what's the current we found? 2. Okay, so it would be 100 watts. Okay, same answer. Okay, so let's move to the another subject here, which is the Kirchhoff's law, or KVL. Ohm's law is not sufficient for circuit analysis. Again, what is the circuit analysis? Circuit analysis, it means we need to find the voltage, the current, the power. What we did in the previous slides, when we solve the practice problem and the example, this is exactly circuit analysis. We determine total power, total resistance, then we determine the current going through in each resistor, and then we find the voltage across each resistor, and then we found the power dissipated by each element, even the power supply. Kirchhoff's law complete the needs tool. So we need the needed tools, we need to solve, we need to analyze. So the Ohm's law by itself is not enough. So we need the help of these 2 laws. One of them they call the Kirchhoff's current law, KCL. It's an abbreviation for K stands for Kirchhoff's, C for the current, L for the law. Same thing for the voltage law, Kirchhoff's voltage law, KVL. KCL will be covered in the next chapter. Kirchhoff's voltage law is based on conservation of energy. It states that the algebraic sum of currents around a closed path or loop is 0. It can be expressed, actually, I should have some mistake here. I want to correct it first. Let me, so I did a correction here. Actually, this was a mistake. concerning the definition of the Kirchhoff's voltage law. So it was a current here, but actually it's the voltages. So it says that the algebraic sum of voltages around a closed path or loop is zero. Remember we talked about the loop. We said that if the loop is a closed path, okay, if we have a power source and we have a resistors, this is called a loop. Okay, so the KVL is applied around the loop or a closed loop, closed path. It's a zero. It can be expressed as, so the sum of like V1 plus V2 plus V3 plus or minus Vs is equal to zero. I'm going to explain this later on. What is the meaning of the sum? This is the sum of the, again, of the voltages around a closed path. So it could be V1, V2, V3, Vs, and so on. Okay, Kirchhoff's voltage law as an example. Consider the circuit show starting at a branch, starting at any branch and go around the loop in either direction. If we start at the voltage source and go around clockwise, the voltages we would see are minus V1 plus V2 plus V3 minus V4 and plus V5 in that order. For example, as we reach branch 3, the positive terminal is meet first. So the voltage is written as the positive. So KVL will yield minus V1 plus V2 plus V3 minus V4 plus V5. Okay, let me see here, let me show you here how to write down that formula, the sum of the algebraic sum of the voltage around the loop is equal to zero. So here's our circuit. Here's the circuit we have. Here are the voltages here, V2, V1, V3, V4, and V5. I want you here to look at those polarities. Those polarities, they are very important here. Plus, minus, plus, minus. Okay. And the choice of the clockwise direction. So this is sometimes you want to assume the current direction either in a clockwise like this or anti-clockwise like this. But most of the time, people, they prefer to assume current going clockwise. Okay, so now I need to write down the KVL. The algebraic sum of the voltages around the loop is zero. Okay, here we go. We start with, let's say, it doesn't matter where we start. If we start with the V2 or V3 or V4 or 5 or V1, okay? So let's start with the V1. So when we start V1, if we look to the current flow, see the arrow here? This arrow at the beginning is going to hit the minus sign. So the sign of V1 will be a minus, V1. See here, same thing. And then when the current comes to V2, is going to hit the plus sign of V2. So V2 will take a plus sign. And then the current will continue flowing and is going to meet or hit the positive. So V3 will be a positive. And then current, when reaches V4, is going to meet or hit the minus. So it will be a minus V4. And then the same thing, when it comes and hits V3, it will hit or meet the plus sign. So 5 V5 equal to 0. Now you can move, if you want, you move, for example, the V1, the negative polarity to this side here, and you could rewrite the KVL as V2 plus V3 plus V5 equals to V1 plus V4. Okay. Same thing, you could do that if you want. Okay, so this will be our, okay, so this is the same as this one here. So, or we can say voltage drops equal to the voltage rises. So voltage rises usually the voltages of the supply voltages. And the voltage drop usually the voltages consumed by the resistance. So that's, sometimes if you want to just do it in this way, the voltage drops equal to the voltage rises, but always I prefer the method I just explained when you come to write the KVL formula. Okay, in drop versus rises, voltage rises occur when we travel across through an element going from minus to a plus. Voltage drop occurs when we go from plus to minus. So same thing as we explained earlier. If you have a component with a plus and a minus and the current goes this way, so when we go from plus to minus, this will be a plus, which is they call the voltage drop here. This is the voltage drop. If we go from minus, if we have, let's say we have a power supply, the current goes from minus to a plus, it will be rise. But again, this is a very confused. I don't want you to go through this definition. The best definition that I found is to use the one that I just used before when I explained the KVL across that loop. Now, a voltage rise is said to take place in an active element. So usually an active element, like the active element usually is the element that will produce the voltage. They call an active element because it gives us energy. Now a passive energy, which is the opposite of an active, is the element that will consume. It will not deliver power or deliver energy or deliver voltage. So usually the power supply we call an active element, and the resistance usually we call it a passive element because again it doesn't produce energy. In fact, it will absorb energy. So this is a definition you might see. Okay, example 4.3. Let's see here what we have in this example. Okay, we are given this circuit and we are specified the polarities of the component. We have minus, plus for the 24 volt, and then we have plus minus for VS, plus minus. And then also we are given the direction of the current. Sometimes if we are not given the direction of the current, we should assume either clockwise or anti-clockwise. But as I mentioned earlier, people, they like to assume the current flowing clockwise. Okay, so we need to determine the unknown voltage Vx. Vx is here. Okay, so again, if we try to use just Ohm's law, we don't know the current and we don't know the resistance. So that's why we need to seek the help of KVL. So KVL and Ohm's law will be the two tools or the two formula that will help us to determine or to analyze the circuit. Okay, so since we need to know what is Vx, so let's see how to apply KVL. So the first step, so now, as I mentioned earlier, that when you solve any problem, you write the formula of Ohm's law and the formulas for the power, I square R, V square over R. Now we need to add the formula of the KVL. Okay, so this is a new information we have to use from now on when we deal with the circuit that has more than one resistor or one element. Now, again, this way that we are going to apply KVL here. So it doesn't matter where we start. let's start with the 24. Again, here's the current. Okay, when you reach to the bottom of the supply, we see this arrow is going to hit the minus sign. So since it hits the minus sign, that means the voltage will be minus 24. And then the current will continue, and when it reach to this positive sign of the Vs, is going to hit the plus. So Vx will be a plus. And then the current will continue and it will meet the positive. So we have to look to the first terminal of the element, not to the second one. Okay, current hits here first, plus, not negative, negative after. So when it hits the plus or meets the plus, then the voltage drop will take the plus sign. Now, again, just use algebra. We have 24, so we can, Vx will be equal to be 24, so minus Vx will be 24, minus 30 will be equal to minus 6. Okay. So the voltage across this, so minus 6 means the polarity has to be switched. Okay, so since we assuming the polarity of Vx, this is a plus, this is a minus, and we found the answer is a minus, that means the actual polarity has to be, this has to be a minus, this has to be a plus. Okay. Okay, let's apply the same information that we had on the practice problem. We need to find Vx, same thing. We are given another element 4 volt and another power supply 12 volt. Again, since there is no current direction assumed, so I'm going to assume in the clockwise direction. Again, we will apply KVL. Okay, so we start, doesn't matter we start, let's start with the 12 volt. So the current is going to hit the minus, will be minus 12. And then the current here is going to hit the plus sign of the Vx. So it will be, Vx will have a plus sign, and then the current will hit the plus sign of the 4. So plus 4 equal to 0. So Vx will be equal to minus 8 or 8 volt. Okay, same answer we get here. Okay, good. So let's move on. Okay, another example. We need to find V1 and V2. So again, these are not given. So in order to find V1, I need to find I and then multiply by 2, which is the resistance. That will give me, so it will be times 2. And the same thing for V2 equal to 3 times I. So the only thing is missing is I. Now again, because this is more than, one element, more than one resistor, I cannot apply Ohm's law, say, okay, 20 divided by 2. Just don't do this mistake, okay? So we have to combine the resistance this first, or we can apply KVL. So let's apply, apply KVL around the loop or the closed path. So again, since the current is being assumed in this direction, so since I is going to hit the minus of the 20 volt and is going to hit the plus of V1 and is going to hit the minus of V2. Again, the sum of the voltage around the loop is equal to 0. So now we have, now since we are looking for I, so now we need to plug for, V1 minus 20 plus V1 is equal to, Now here I should make a correction here because V2, since the current I is hitting the minus, so it would be a minus 3 here. So V1 is equal to 2I. Then we have a minus, and then we open parentheses, and then we plug for V2. So V2 is equal to minus 3I. Okay, that's equal to 0. So that one will be, so this will be 5 because minus times minus is a plus. 3 plus 2 is 2. So it will be minus 20 plus 5I equal to 0. Or we could say 5I equal to 20, or I equal to 4 amps. So after we finish, after defining I, we will be able to determine the voltage V1. So V1 will be equal to 2 times I, will be 8 volt, and V2 will be a minus 3 times I, will be minus 3 times I is 4, so will be minus 12. Okay, so is a 12 minus 12 is the 8. Okay. So again, as I said, you have to follow the direction of the current and have to pay attention to the polarity of the elements. Okay, let's see here how to solve the practice problem. Okay, and what do you think here? We need to find V1 and V2 in the circuit. Okay, what is the first step we do? Okay, apply KVL, good. So step 1, apply KVL around the loop, good. Start from at 10 volt, that's fine. You want to start with V1, it's fine. So minus 10 plus V1 minus 8 plus V2 equal to 0, equals to 0, good. Again, we hit the minus, we hit the plus, we hit the minus, we hit the minus. Okay, so I did a mistake here. Okay, let me correct that mistake. So instead of writing minus, because I hit the minus, I did a plus. Well, let's correct my mistake here. Okay, so it will be minus. Why? Because the current, see this arrow, it hits the minus. Now we need to apply for V1. So if we apply Ohm's law, so remember I said that we need Ohm's law most of the time. Ready? So now I need to plug for V1 and V2. So V1 is equal to I times R1. Again, we have to use the resistance that we are looking the voltage across it. We cannot use different resistance. We have to use the current flow in that particular resistance. So I times R, so R is 4, so R for I, and the same thing for V2 will be I times R2. So I is unknown, and the resistance R2 is 2 times I. And then now we can plug this value in here. So minus 10 plus V1 is 4I, and then V minus 8 minus V2 is 2I, equal to 0. So now we have to collect the similar terms. So minus 10 minus 8 is minus 18. And then we have plus 2I equal to 0. Okay. So minus 18, so I will be 18 over 2. So I equals to 18 over 2, which is 9 amps. So let me check again Okay, I'll show you here. I covered a mistake here. I'll show you where is it. See V2 here? The V2, it's, if you look to the V2 here, the I is entering to the minus sign. So here, what I did here, I should add a negative equal negative here. So this is, will be a minus 2I. So when we plug into in this voltage here, so this minus and the minus here, so minus times minus is a plus. Okay, so this is will be 6. So 4I plus 2 is 6. So then I will be 3 instead of 9. So this will be 3 amps. Okay, now after we determine I, we'll be able to find V1. So V1 will be I times 4, which is 4I. So 4 times 3, so will be 12 volt. And V2, which is here, V2 is minus 2 times I, and I is 3, so minus 2 times 3 is 6. So V2 is equal minus 6 volt, and this is will be the same as the book answer. Okay, in this example, the difference between this example and the previous one, we are not given the polarities of the resistance. Okay, here's how we determine the polarity. Now, we know that by definition that always the current goes from a positive, from a high voltage or a positive to a negative. So since this I is going up here, so then this is a plus, this is a minus. Same thing here. This is a plus, this is a minus, this is a plus, this is a minus. Okay, so this is the first step you do if the polarities are not given. If the polarities are not given, we must assume, or we must assume, first, if sometimes even the current direction won't be given, but again, we have to assume it in the clockwise or even in anti-clockwise, but it's easier to people that get use of applying current in clockwise. So when we do applying or assuming the current in clockwise, then we have to put or mark the polarities of the elements. So again, current goes from bottom to top. So the bottom one has to be a plus and this one has to be a minus, and the same thing. So if we, for example, let me show you, if we assume the current going this way, so then this has to be a plus, this is a B minus, this has to be plus, the minus, because the current going this way. Now, this one you cannot touch. If you have any element, it's pre-marked, whatever the the polarities are already marked. You cannot change them, regardless of the current direction, okay? So in this example, we cannot charge. You cannot change the polarity of the power supply because it's already being marked. Here's a plus, here's a minus, you cannot change. It doesn't matter what is the current direction here. Okay? And this is a rule here, so you cannot do that. Okay, so so here we are asked to use the Kirchhoff's voltage law to determine the current I. So again, we apply KVL. Again, plus minus, plus minus, plus minus. So minus 60, and then plus 30I, plus 30I. Let me just write it down. Very good. 30I, and then plus 20I plus 40I equal to 0. Okay, so we add, so this is 30 plus 20 is 50, 50, this is 90, so it will be 90I equal to 60, so I equal to 60 over 90. Okay, this is this is one of the method. Now method number one, this is probably method number two, or you could use find the RT, so you don't need to use the KVL. We could use only Ohm's law, but before we use Ohm's law, we have to combine all the resistors and finding the RT. So this is what it's in this method here. So we can find RT, which is adding all these resistors, 30 plus 20 plus 40, just equal 90 amps, 90 ohms, sorry. And then we apply the Ohm's law. So Ohm's law, so we have I equal V over RT. Okay, again and again, I wanna just warn you, give you a warning. When you find I and you wanna apply Ohm's law, you cannot say I equals to 60 over 30. This is totally wrong. Or you can say 60 over 20, just take one resistor. You cannot apply. When we apply Ohm's law, we have to find the voltage across that resistance and the resistance, and then we apply Ohm's law to find I. But because you are given 60, so 60, it's not applied only to the 30 ohms or the 20 ohm by itself or the 40 ohm. It applied to the total. That's why we need to find RT, and then after that we apply Ohm's law. This is very important information you should know. Practice problem, again, this is the method number two. We already explained it earlier. The same thing here as I did in the previous one. Okay, in practice problem, again, here is the current direction, plus, minus, plus, minus, plus, minus, plus, minus. Again, because the current going this way, so always the tail will have, again, here's the going this way, current going this way, okay, or going down. Here's the tail is the plus, arrow is the minus, because the always current goes from a higher potential to a lower potential. And since these polarities are not given, so then we have to assign this polarity. So if the polarity are not assigned, the first step you do, step one, assign polarities of the resistors. Okay, voltage source, you cannot change them. Keep the polarity as given in the problem. And then you can apply, then step two, apply Ohm's law, KVL. Step two, apply KVL. How? Minus 120. Why is minus? Because the current is going to hit first the minus, and then plus I times 40 plus 100 I plus 10 I plus 50 I equal to 0, and then you add all this, and then you find I equal to 120 over the sum of those three. Again, you could use the method number one as in the previous example by finding this R of t here, or you can say RT is equal to 140, 50, and 50 is 200 ohms, which is R1, which is 40 plus 100 plus 10 plus 50, and then you find I is equal to 120 over 200. So there's two ways or two methods to solve this problem here. Voltage source in a series, again, sometimes we are given more than one voltage in a series. So if we need to find, the voltage between A and B, and if we apply KVL here, so since we are hitting the minus sign, so it will be a minus VAB, and then plus V1. So this is similar to as if we have resistors here. So again, here's the loop. Then you could, if you want to put voltage source like this, you call VAB. VAB. Here's the loop, so we're hitting the minus, so minus VAB, we're hitting the plus V1, V2, and then we're hitting the minus, so it will be V3. So the voltage, the total supply voltage is V1 plus V2 minus V3. So again, it's very similar to the resistor. Okay. Voltage division, this is sometimes, you know, there is an easy way to find the voltage at any elements in the circuit that you want. Okay, so let me see here. Okay, voltage division, series resistors are often used to provide voltage division. That means those, you know, those resistors, they divide the voltage. If we have a voltage Vs, let's say 100 ohms, 100 volt, and we have 5 resistors and they are equal, so that 100 volt will be divided across those resistance equally, because those resistance are equal. So each one will take like 20 volt, this will be 24. So that's why the series resistors are often used to provide voltage division. We try to divide the supply voltage across those resistors. If we apply Ohm's law to each resistor, the voltage drops again. V1, if this is a V1, this is a V2, this is V3 and V4 and Vn. This is Vn, again plus minus, since we assume current going this way. So V1 will be equal to I times R1, and then V2 will be I times R2, and so on. Vn will be equal to I times Rn, and so on. So this is, again, as it says here, indicated here. Now R equivalent, again, the Rn or R equivalent or R total will be R1 plus R2 plus R3 until we finish all the summing all the resistors here. Okay. Voltage division. If a voltage V is applied across the resistors, the current through them is equal to V over R. Again, we go back to, if this is a voltage V, the supply voltage, and there's a resistors here, R1 and R2, Rn, and you know, whatever that resistance we have. So then R3, and this is Rn. Again, we add all the resistance, so I equal to V over R equivalent. Now, if we want to find a voltage at any resistors, okay, we need to find like V3. So what we do, we just take V over the total resistance, RT or R equivalent, and then multiply by the resistors of that voltage here, by that element. This is what they call the voltage division. So if you have, I'll show you an example. If you have multiple resistance, R1, 2, 3, 4, 5, 6, until R, let's say R9, and ask you find the voltage across the resistance 9. So then what you do is you find, you take the V supply, divide by RT, so you add all the resistance from 1 to 9 or 1 to 10, and then multiply by the value of that resistance, which is number 9. If I ask you to find the voltage across the resistance number 5, you do the same thing. You take V over I, RT, which is I, V over RT, or R equivalent, multiply by R5. And then the same thing. So simply, the voltage division is very simple technique to determine the voltage across any elements you want. Okay. So let's say if we have two resistors here, we have R1 and then R2, then we have the supply voltage V here. Here's R1, here's R2. So we need to find V1 and V2 using the voltage division. So again, it's the same way. We just apply Ohm's law. We apply, you know, and we find I. equal to V over R1 plus R2. And then we need to find V1. So V1 will be I times R1. So I is V over R1 plus R2, which is again, this is RT or R equivalent, multiplied by R1. So simply we apply Ohm's law twice to find the V2 and V1. Same thing for V2 is equal to what? V2 is equal to I times R2. And I is the voltage divided by R equivalent, which is R1 plus R2. So this will be R equivalent will be R1 plus R2. So again, if we have two resistors in series and you want to find V2, so what we do, we take the supply voltage divided by the total resistance multiplied by the resistance that we are looking the voltage across it. Here's an example. We are given R1 and R2, and we ask to determine, find the voltage across each resistance. Again, V1 is equal to V over R1 plus R2, and then multiply by R1. So again, V is 18 over R1 plus R2 is 9 multiplied by 4. Okay. And the same thing for V2. So V2 will be, again, it's V over R equivalent, which is R1 plus R2, multiplied by the resistance 5. Okay, and V is 18 over R equivalent, which is R1 plus R2 is 9, multiplied by 5, 10 volts. This is our second. Okay, let's check here. We have R1 equal 30 and R2 equal 20, and we need to use using the voltage division. So again, voltage division is driven from using Ohm's law twice. The first one is to find I, so 100 over R equivalent, this is I, and then we use Ohm's law across each of these resistors to determine V1. Or we can use the formula directly of the voltage division. So we need to find V1 is equal to V over R equivalent multiplied by R1. So V is 100, R equivalent is R1 plus R2 is 50, multiplied by 30. And the same thing for V2, so it will be V over R equivalent times, okay, so this is Ohm's law, voltage over total resistance, this is I, and then we take this I and multiply it by the resistance R2 to get the voltage across the R2 or V2. Okay, use the voltage division rule to find V1, V2, and V3. Again, it's very similar to the previous one. The only difference is that we have 3 resistors here instead of 2. So we're looking for V1. So V1 will be 60 divided by RT, which is R1 over, V over R equivalent. This is will become I. Then I multiply by R1. We get, so this is an I, and this is an R1. So again, this is Ohm's law. So here we apply Ohm's law, and then here applies Ohm's law second time. And the same thing for V2. So V2 will be V over the total resistance will be I, then I times 12. So again, as I mentioned earlier, voltage division is driven from using Ohm's law twice across the segment. First time, we find I, which is V over RT or R equivalent. Then the second, when we apply Ohm's law to find V1 and to find V2 and to find V2. Again, this is the same. We take V1 is equal to 50 over R1 plus R2 plus R3 plus 15. And then, so this is I. Then multiply this by 25 to get, so when you determine this one, you don't have to repeat it when you determine V2. So you take this value, multiply by 10, same value, and because this value is constant, the same, because I is the same, and then V3 will be the same. You take this value, multiply by this value here multiplied by the 15 here, okay? So you should get the answer that we have in the book here. So go ahead and practice this problem exactly as we saw in the example. Ground connection, like measuring distance, voltage must be measured from reference point. The most common reference point used is the ground. So always the negative side of the power supply is connected to the ground. So what they use a rod made of copper, and they insert this rod inside the ground, and they connect it to be sure that the negative side of the power supply, it has a 0 voltage. This is why this reference point is referring to as a ground. Grounding electrical equipment that is connected to ground is said to be grounded or earthed. Part of the ground of any building is a wire that is connected to the large metal rod driven deep into the ground. This ensures a good connection to the ground. Proper grounding is vital to making electrical equipment safe. Imagine an electrical device sitting on a wooden table. If the device is damaged, a charge might accumulate on the frame of the device, since the table will not conduct electricity. Any person touching or possibly even just going near the device may get a serious shock. In older homes, the incoming water pipe was used at grounding as it was galvanized steel. However, with the rise of plastic pipes, this is no longer the case. Any person touching or possibly even just going near the device may get a serious shock. In older homes, the incoming water pipe was used as a ground as it was galvanized steel. A copper rod 4 feet long is inserted into the earth, is becoming the grounding connection. Then the grounding point is connected to the neutral wire inside the electrical panel. Here is the symbol of the grounding. A ground is a point of a reference. We attach the value of 0 to ground. The 3 symbols shown below are represent ground. Earth ground is shown in A and B. Chassis ground is shown in the chassis ground is shown in figure C. So this is the actual ground here. We see here that is a rod is about 4 feet long. That piece of rod has to be inserted into the, this is 4 feet long. This has to be inserted into the ground, and then they take a wire, a copper wire, and connect it to the neutral or the negative side of the power supply in the panel. So this is the panel in our homes. These are the breakers, have to be connected. It's like a switches, but it's when there's any fault or any mistake, that breaker will turn on, turn off by itself, automatically by itself. It trips by itself. Okay, so this is the end of chapter 4. So next time, actually chapter 4. Yeah. So next time we'll talk about chapter 5, which is the parallel circuit. Thank you again for watching this video, and we'll see you in the next video.